Hello, everyone. In the following 10 minutes, I will give you an overview of our paper. This is a joint work with Yang, Xiaokui, and Bolin. So we study the problem of streaming data collection on the local differential privacy. First, let's motivate our setting. So in our setting, there is a set of users. Each has a stream of data items. Here, each data item represents the status of a user on a specific time step. For example, let's say each user is an online shopping website. Then the status of the user on step I can be the daily number of visitors to the online shopping website on day I. For example, let's say the first user is the Amazon's webpage for electronics. The second user is the Amazon's webpage for groceries, etc. Now let's say some untrusted data collector, say Walmart, wants to collect the status from the users to estimate the daily average number of visits to all shopping websites. Of course, if you are Amazon, you do not want to give out this data directly to Walmart because he is your competitor. So what can a user do in these kind of scenarios to achieve some level of privacy while allowing the untrusted data collector to learn something useful? So local differential privacy has become a standard approach in these kind of scenarios. The basic idea is that each user independently adds some noise to her data before sending it to the data collector. The data collector, on receiving the noisy value of the data, cannot infer directly the original data. Hence, privacy is achieved. On the other hand, when the population is large, the overall error for the population mean is actually very small. So the data collector can learn something useful. For example, let's consider the Gaussian noise. Then each user adds a Gaussian noise of some value to their true data item. We say that a mechanism is epsilon delta differentially private if the mechanism always produces similar outcomes regardless of the inputs. Here, to achieve epsilon delta local differential privacy, it suffices to set the scale of the Gaussian noise, namely the standard deviation of the Gaussian noise, to be roughly the range of the data over epsilon. And this is actually the baseline solution for streaming data collection with local differential privacy. And how can we improve the baseline solution? We have an observation. The observation is that for common data streams, the difference between neighboring data items can be very small compared to the overall range. Take me as an example. This is my daily number of pickups for mobile phone. So on July 28th, I had 156 pickups, and on July 29th, I had 147 pickups. So there is a decrease of 9, but this difference is very small compared to the overall range, which can be up to 1,000. So we can see that in practice, this difference is indeed very small. So how does this observation help us to build a better mechanism? So on the top, we have the baseline solution. The idea is that to achieve epsilon delta differential privacy, at every step, each user independently adds a Gaussian noise of scale calibrated to the range of the data item over epsilon. So we put the original data in the blue box and the noisy data in the yellow box. And at the bottom, we have our solution. Let's say at the ith time step, we have already released the previous data item from the I-1 time step in some way. And when the new data item comes, instead of releasing this new data item by injecting a Gaussian noise, we can actually release the difference between the new data item to the old data item. And to achieve the same level of local differential privacy, it suffices to add a noise only of scale roughly the range of the difference over epsilon. And since post-processing preserves differential privacy, we can reconstruct this new data item by reusing the old data item and the freshly perturbed noisy difference. And this gives us a naive approach. Actually, this naive approach is even worse than the baseline solution. To see why, let's look at the ICE data item. So to reconstruct this data item, we have to add the first noisy data item and I-1 noisy differences. And all these independent noises actually makes the error in the ICE data item much larger than that in the baseline solution. So instead, we consider a more general approach, the correlated Gaussian mechanism. So in the first step, we release the first data item in the same way as the baseline approach. And next, in every subsequent time step, we first introduce the notion of a reuse ratio. And then based on this reuse ratio, we add noise to the convex combination of the new data item and the difference between the new data item to the old data item. And to reconstruct the new data item, we can simply reuse the previously released noisy old data item and this freshly perturbed convex combination of the new data item and the difference. And we can optimize this error at each time step with respect to this reuse ratio Ri. And here is the comparison between our mechanism and the baseline solution. So for the baseline solution, we assume nothing but bounded data items. We can say without loss of generality, each data item is bounded by a unit sphere. And for our mechanism, we say that in addition to the bounded data item select, bounded data item assumption, we also have that the difference between neighboring data items are close. In practice, we can enforce this constraint by clipping the out-of-range data items. And by enforcing this constraint and then exploring this constraint, our mechanism improves the error by 4C times. Here C is the parameter for the correlation constraint. For example, if C equals to 0.01, then the utility improves by 25 times. And now we move on to experiments. So here we use a Kaggle web traffic time series, which reports the daily number of visits to approximately 80,000 web pages. So here we can imagine each web page is actually an online shopping website. This corresponds to our motivational example in the beginning. And here each data item is bounded by 20,000. And we report the mean squared error for the daily average number of visits for the baseline solution and our mechanism under epsilon equals to 0.25 and delta equals to 10 to the power of -5. And for our mechanism, we enforce a correlation constraint of C equals to 100. And here the red line represents the error for the baseline solution and the green line represents the error for our solution. Note that for our solution, the error comes from two independent components, the error due to clipping and the error due to the additive differential privacy noise. So we can see that the error due to clipping is actually much smaller than the error due to the differentially private noise. So the performance of CGM is aligned with our theoretical analysis. And hence overall, CGM improves the data utility for the baseline solution by roughly 50 times in this case. And to conclude this presentation, we study the problem of streaming data collection on the local differential privacy. And we observed the natural correlation between neighboring data items in a data stream. And we devise a mechanism that utilizes this correlation to improve utility. In theory, the stronger the correlation, the larger the improvement. In practice, our mechanism also consistently outperforms the baseline solution on the various settings for the correlation and privacy parameters. And that's all for my presentation. Thank you.